The following presentation was recorded at the 2025 Southeast Linuxfest in Charlotte, North Carolina. It is licensed under a Creative Commons license. For more information on the Southeast Linuxfest, visit www.southeastlinuxfest.org. Come join us next June.
All right, I think we've got one more minute before we get going. For anyone who's just walked into the room the past couple minutes, if you want to follow along on your machine with the slides, with the capture files we're looking at, with anything else, hit that GitHub link. That's going to be everything you need. I got 5 o'clock. Are we streaming it okay? Good to go? All right. All right, so everyone, thanks for coming out and coming in to learn a little bit about Stratoshark, this brand new tool from the Wireshark Foundation. My name is Josh Clark. I'm going to be your tour guide today as we dive into not just packets, but now system calls. The agenda for today, I'm going to tell you a little bit about myself, a little bit about Wireshark and Stratoshark, and then we're going to dive into what are system calls. These are the foundational things that we look at in Stratoshark, just like we look at packets in Wireshark. And we need to understand what they are so that we can better understand how best to use this new tool that we have. I'm going to go into how Wireshark and Stratoshark grab the data that we ingest and then examine in those tools. And then we're going to finish off with a demo. So about me, I have both my bachelor's and master's degrees in computer engineering from North Carolina State University, go Wolfpack. And particularly in grad school, I ended up spending a bunch of semesters breaking Linux. I got into these network engineering classes where the semester project would be choose some narrow aspect of networking, TCP congestion control, the algorithms that routers use to manage their buffer space, something like that, and figure out a way to make it better. Now, I never had access to like the Cisco source code so that I could try these things on the big Cisco routers, anything like that. The platform I had to do that experimentation on was Linux. Because Linux, if you go into the commit history within that net directory of the kernel, it is 30 plus years of development of networking. And I found that absolutely fascinating, and it was a privilege to go in and break all of that code trying to make it better. But I came out of grad school with not just some understanding of networking, network protocols, why network protocols work the way that they do, but also some understanding of Linux internals. What is happening in the kernel? How does Linux process packets? And I've made good use of both facets of that knowledge, leading to my kind of current job. I'm out in Seattle as a performance engineer for a pretty big bank. And I know you heard Seattle and thought, this is not the Southeast. That doesn't make any sense. What's he doing here? And the truth is, I am actually moving to Columbia, South Carolina in just about a month. So I'll put the call out right now. If you're in the Columbia area, you know people in the Columbia area, I would love to meet you. Come grab me after the session. If you're watching this streaming, go to my website. My contact information is there. Love to start getting to know some people in the area. But about my day job here, what I do as a performance engineer is I just kind of roam around all the different systems that the bank has and try to find where the bottlenecks are and try to remove those bottlenecks. It's an extremely fun job. I really love it. And in my workflow, I very often start with Wireshark. With the right packet capture and the right set of eyes looking at it in a distributed system, you can do things like reverse engineer that whole system if it's not well documented. You can map out microservices and see what's going where. You can do timing analysis and get a better understanding of how long things are taking. Is this slow thing because of network delay or something on the server or something in the application? You can see all of that from a packet capture. And once I do that and identify what the slow component is, then we dig into more of the Linux-based performance analysis tools. You do the simple things like top, make sure you're not running out of CPU or memory. You do things like df to make sure you're not filling up a logging file system. All those simple things. And then you get into the complex strace, bpf trace, code profiling tools, everything else that's in that world. And for the longest time, I've had this like minor gripe because all of these tools, they're fantastic. They do one thing really, really well. But when I'm in a situation where I need a week's worth of data to see how things change over time, well, that means I'm setting up a cron job to run every couple minutes, and then I have to choose which of these tools that I want to run. Is this an strace and netstat problem, or is this a df and some other file system tool problem? And if I make the wrong decision, I've wasted a week's worth of time looking at the wrong data. I've always wished that there was a less fragmented set of tools to look at Linux performance. And really in my head, I've kind of wanted, I really want Wireshark, but for Linux. I want to look into Linux with Wireshark. And that's exactly what Stratoshark is. And it's why ever since I first heard about it about 3 years ago, when it's been started going into development, I've been really, really excited about it. We are on version 0.9.2 right now. The version 1 release is supposed to be in just a month or two. And I've been playing with it for about 6 months, trying to see what I can see and what we can get out of it. So I mentioned Stratoshark looks at system calls. But what are system calls? And I think my favorite way to explain this is by looking at some code. So when you learn a new programming language, one of the first things that you do is you learn how to open a file and read from it. And that's the Python code that we see here. Really simple, 2 lines. First line we open the file, second line we read. But underneath those 2 lines of code, there is a world of complexity. I mean, just imagine you have this file.txt. Where is it stored? If it's on my computer here, this is some sort of soldered memory or it's a soldered storage. If we're on a desktop, maybe it's an NVMe, maybe it's on a SATA drive, maybe it's on a SAS drive. All of those are slightly different protocols, slightly different device drivers, and we don't see any of that in this code right here. What if it's on network storage? There's a whole network layer, and then you have to talk NFS or Samba or something like that. There's a world of complexity under these 2 lines of code. But hey, it's Python. It's a high-level language. You write pseudocode, and then it runs, and it works just fine. So Python's got to be handling this, right? What if we look at another program? What if we look at something like C? After all, Linux is written in C for the most part. We surely can't hide from any of that complexity there. And so the C code, I mean, there's more stuff here. We have to allocate memory for the file contents. We have to end that array with a null character, so it's a valid string and all that stuff. But there's still nothing about the different drive types, nothing about USB. So where is it? That's what the operating system does. Linus Torvalds at one point said that about half of all of the code in the kernel is just device drivers. So the operating system deals with all of that complexity and then allows all the applications running on that operating system to access all of those bits of hardware, all of the functionality in all of that hardware. And it does that with an API, just a set of function calls, your opens, connect, read, write, close. And when it says many more, the total's about 450 right now. So there's a lot of stuff going on that the operating system implements for all of the software that runs on top of it. And that API, those 450 plus calls, those are the system calls. If you have a CS degree, you've taken an operating systems course, you've probably implemented a good chunk of those. So system calls then are functions that applications or processes running on an operating system call in order to access elements of the hardware, the chipset, the network, whatever else is going on. I've found that having a good reference handy for looking at those 450 different calls is really important. I haven't gotten to the point where I've memorized all of them yet, and I probably will never. This is a really nice searchable table that takes you right to definitions for all of those different calls. I have this open in a browser tab anytime that I'm using Stratoshark because I really need that reference. Okay, so we know what system calls are, but how do we get them? I think the story of how we actually capture system calls starts with Wireshark. So this is a basic diagram of the Linux networking stack. A packet that you receive into your computer starts at the bottom, that physical layer, hits the link layer where there's device drivers, the internet layer where it deals with IPv4, IPv6, the transport layer where it does TCP, UDP, and then it goes through a socket to talk to some application that is in user space, not in kernel space. Back in the early 90s, there were a couple researchers at Berkeley who decided they needed better data about what's happening on the network. So they wrote some isolated code in the kernel that's sitting right next to those device drivers. And anytime a packet comes in or out of that interface, that little bit of code makes a copy of that packet, applies some filtering logic to it to decide, is this worth sending up to that user space program that's going to log it, going to do statistics on it, or whatever else is happening. Now, because this is a system from Berkeley that applies filtering logic to packets, they very creatively called it the Berkeley Packet Filter, or BPF. Now, there is a user space library to control access and make calls to that BPF code, and that's libpcap, the packet capture library. And everything that we do with packets is built on BPF and libpcap. TCP dump, Tshark, Wireshark, all of the other tools that are out there to give you insights on what's happening on the network, what's happening with packets, all stems from this little bit of stuff. So what if we take this idea of having isolated kernel code that is sitting in the right place to get the right events and take it out of the network stack and put it everywhere in the kernel? That's what we get. This is how we get our system call events. There's a couple different ways, couple different supported ways. There's kernel module and there's a eBPF probe that both work interchangeably. And then they will grab events and they will send them up to user space to this libscap and then libsinp. Libscap is the system capture library. And let's say it gets some event. We have my Python code that is opening a file. That call makes its way through the kernel, through that kernel module, and then up to libscap. Libscap sees a process ID. My Python process is process ID 12345. And it sees the file that I'm opening is a file handle, not a name. So that doesn't really help me when I'm going back later, because who knows days later what process ID 12345 was. So that's why libscap sends its events up to libsinp, the system inspection library. What that does is it goes and takes that event and looks up, okay, what is process ID 12345? Oh yeah, it's Python. So it enriches the event data that's coming from libscap and then sends it on up. Now, right now, unlike Wireshark, Stratoshark has no native capture capabilities. You can't open up Stratoshark and say, capture my events. The tool that does that is called Sysdig, and that GitHub link there is the Sysdig repo. I'm not going to go over Sysdig today. Their GitHub page has a fantastic wiki that gives you all the installation instructions, run instructions. If you want more of a step-by-step guide of just getting running so you can look at Stratoshark stuff, you can go to my website. I have a post called Getting Started with Stratoshark, and it walks you through all of that. So we use sysdig installed on the Linux systems to get our, instead of pcap files, scap files, and then we use Stratoshark to open them. Any questions so far? Yes, sir. So the question here is about the DPDK library, which I think you might be talking about XDP, the Express Data Path. That one, so one of the insights that eBPF enabled when you took that idea of let's isolate some kernel code and use it to do basically tooling and monitoring. Let's take that, extend it to the whole kernel, and we'll call that Extended Berkeley Packet Filter, eBPF. And then people started doing things like, well, if I can just look at whatever I want and execute arbitrary code in this eBPF space, I can do really interesting things in the kernel without having to do basically a memory copy from the kernel memory up to the user memory. The Express Data Path, or XDP, is one of those things. So for example, Cloudflare, that DDoS mitigation company, they do most of their DDoS detection and mitigation using the Express Data Path. So all of their hundreds of thousands of rules and regular expressions and everything, they're executed in the kernel without having to copy anything up into user memory. So that's one of those things. We might see updates to rules if we're trying to analyze things with XDP. So when Cloudflare's user space program says, I need to update this rule set, we might see that call in Stratoshark. But because XDP is entirely executed in the kernel, there's no calls to other programs. And so we won't see that. Yes, sir? So the question is, did sysdig and this capture capability not exist before eBPF? And the answer is no, because there are two ways to capture stuff. There's eBPF, and then there's kernel modules. Kernel modules are essentially bolt-on code that you can install basically from a user program. You do a reboot, and then all of a sudden you have all this extra code. That was the primary way that when I was in grad school, I was trying to bolt on extra networking functionality and breaking the system. So writing that extra code, using the existing hooks that are built into the kernel, and doing the instrumentation based off of that is the original way that sysdig got those system call traces. But the modern way is way more efficient with eBPF. And if we remember the nice CrowdStrike outage, which was Windows and not Linux, that's kind of the risk of running code that isn't being verified separately at the operating system level. Kernel modules are roughly equivalent to how CrowdStrike has been working on Windows. eBPF includes a verifier that makes sure that code will not cause the system to crash. So it's faster, it's safer, it's the way of the future. But we could still do this before eBPF was a thing. Anything else before we get into the demo? Yes, sir. So the question was, what does SINP stand for? And that is the System Inspection Library. All right, demo time. If you're following along and you have Linux on the desktop, I am sorry you won't be able to follow us to Stratoshark because you've got to compile from source until the package maintainers for the distros catch up. You can follow along on Wireshark though. So here's Wireshark. This is that HTTP packets file. And if you've never used Wireshark before, let me walk you through what we're seeing. So this main pane right in the middle spans the full width is called the packet list. Every row on here is a different packet that is going over the network. On the bottom right, we have what's called the packet bytes, and this is just the hex dump of the currently selected packet. So if I move around, we can see that all changes. So this is exactly what you would see in a hex editor. And then on the bottom left, we have what is Wireshark's view of that packet. Wireshark has a really intense dissection engine. I think supports more than 250,000 different protocols at this point. So, and it goes through and it takes that hex data. So we can see, say, this field right here. That's the hex that it's associated with, and it knows what exactly it is and what it means. So, basic tour of the interface. And if you're following along, I have a couple columns here that you don't. You can get them, but I want to point out what they are real quick. So first is this delta conversation column. My second column here is the time, so it starts counting up from the first packet. And what the delta conversation column does is it takes, for example, for packet number 6, that timestamp is basically 1.5 milliseconds. Packet 5, the timestamp is 0.9 milliseconds. If we subtract timestamp of packet 6 from packet 5, we get a difference of 618 microseconds. And if you're doing the same kind of performance analysis that I do regularly in Wireshark, this column is your best friend. The other thing that I have over here that you may not is this nice packet flags. So think about TCP flags. You've got your SYN, you've got your ACK, your FIN, your reset, your push, all those. This is a nice, easy view of what they are. So I can see from a glance, this right here is a SYN ACK. I've got the S and I've got the A. If I scroll down to the bottom, well, those are clearly FIN ACKs. So I've got the F and the A. So I use these all the time. If you're starting to get into Wireshark and packet analysis, recommend setting both of those up as columns that you have regularly. Now let's start looking at some of these packets. Now, there we go. It's very important to remember that packets are a lot like ogres. And of course, ogres are a lot like onions. They have layers. We think of packets in layers. So the innermost layer of this packet is the Transmission Control Protocol, or TCP. The layer outside of that is the Internet Protocol, so IPv4. And outside of that is Ethernet. And so if we look in here, we have a source port and destination port. So this is referring to, hey, this is HTTP traffic. If we look at this layer, now we're seeing IP addresses. And if we look at this layer here, now we're seeing MAC addresses. And as the contents of the packets change, the layers change. So this packet here has an HTTP request in it. So now we see that HTTP layer. Now let's take a look specifically at the start of this conversation, because I want to show off what you can see with Wireshark. So the start of this conversation, we're going to look, see the source IP is 192.168.64.1. The destination is 64.3. So we know who's talking to each other. That's good information. And I can actually expand this TCP header. We can see the source port, 58219. That's the ephemeral port that the client's presenting. So this is probably coming from a browser, terminal, or just something on that client. Destination port is 80. And if you've been studying for Security Plus, Net Plus, CCNA, any of those certs, you know that means HTTP, unencrypted traffic is ahead. And we see some other things. So we get a sequence number and acknowledgement number. One of the features of TCP is that it guarantees delivery of your traffic. And it keeps track of what traffic has been delivered and not delivered via the sequence number and acknowledgement number. We also see we have a window. The window indicates how much data can we accept at one time. Along with that, we have some options. So we see the maximum segment size of the client is 1460, so that's the amount of data that I can shove into one packet and still send it to the client. The window scaling is an optional feature that lets us increase that window size and receive more data at once. And then we have timestamps and selective acknowledgement here. Both of those are features that, if there is packet loss, helps that transmission recover just a little bit faster and maintain your network speed. So a lot of good data here. We know just from looking at this one packet, we have an understanding of the capabilities of the client. We have an understanding of how much data can be in one packet in this conversation. And if you look at the server side, now we see, okay, source and destination IP addresses are reversed, source and destination ports are reversed, and now we see all of these settings for the server. So the server has the same maximum segment size, also permits SAC and timestamps, so it does that error recovery well, and it actually has a higher window scaling value, which means it can receive more data, a greater number of packets at once. So good stuff here. And then we can get into our HTTP. So because this is not an encrypted session, we can see it. And we can see that this is a get slash. So give me the root file of whatever this website is. We can see the website it's asking for is just the IP address of the server because I was too lazy to give it a host name. And we can see the user agent here is curl, which means I did this from the command line, not from a browser. Now what we can see here, the next packet we get is now from the server to the client, and it has a length of 0. This is a message that says, I got your request and I'm working on it, just hold on. And the next one we see has a bunch of data in it. This is the start of the server's response. So this is going to be whatever root file is in that website. And if we can look at this, this is the one that I pointed out has that 618 microsecond response time. That means the server spent 618 microseconds before it started sending the response to the client. Now, 618 microseconds, fantastic response time. I would love to see that in all of my production systems. I don't. I would accept 500 milliseconds. That's not too bad. As soon as it starts getting over 700 milliseconds, I start to worry. If it's over a couple seconds, I start calling people. Just to give you an idea of the scale. And now we can see that the response came back in 1, 2, 3, 4, 5, 6, 7, 8 packets. And we can see that Wireshark tells us that it reassembled 8 different packets in order to show us this response. And we can see the headers. It was a status code 200, which means it was fine. I was using Apache. I did this a couple months ago. Right, we have all that good data, and then we actually have the HTML that we can snoop on. And if we take a look at that, Apache 2, Ubuntu, default page, it works, which means I was as lazy as it was possible to be and just started Apache and did change no defaults at all. All right, so from here, we have an idea of the networking capabilities of the client and the server. We have a timing response of how long the server took to serve the response. We know how many packets that response is broken up into. And if it's unencrypted, we can see what that response is. Now let's look at the exact same transaction. I captured this the exact same time on the web server in Stratoshark. So we can see the window is very similar. Right across the top, we have now the event list or the system call list. The bottom right, we have the event bytes instead of the packet bytes. And on the bottom left, we have the event details, which is how Stratoshark is dissecting this event that we have. And so I'm going to scroll down a little bit. There's a lot of stuff that happens. And all of a sudden here, I see something interesting. this column right here is the file descriptor name. So we hear everything in Linux is just a file, and that includes network connections because we are treating this network connection here just like a file. So we can see this network connection's name, 192.168.64.1:58219. Interestingly, that is exactly the source port that we saw in Wireshark. So this is clearly the same thing. We can see it's talking to 64.3.80. So this is the start of this connection. Now we can see that the event name, so this is the particular system call that's being used on this file descriptor, is an accept for. That means I am accepting an IPv4 connection. And then we see these like little carrots here. So, you know, when you run a little bit of code, you're calling a function. If you've ever used that debugger and you've done the step into and step out of, the right-facing arrow is the step into the function. The left-facing arrow is the step out of the function. So this is the process's request to the kernel. This here is the kernel's response to the process's request. So we see Apache said, I am ready to accept a request, and the kernel said, yep, here you go. And what I find really interesting is just before that, we have this response for an event called epoll pwait. What this is, I had to do a lot of research on this one. This is basically a message when the process calls that function, it is saying to the kernel, I'm going to sleep because I don't have anything to do right now. Wake me up when there's something to do. And the response comes when it's ready to be woken up. So at some earlier point in time, Apache said, I'm not responding to anything, nothing's going on, I'm going to go to sleep. And then as soon as the client made that network connection up to the web server, the kernel returned that epoll pwait, and Apache knew time to accept something. Some other stuff happens, but now we have a read, this read response from this file. And we can see in the event bytes, this is our HTTP request. Nice. And if I come down a little bit, we see a write. And this write here is now our response. So we can even see in here, modified from the original Debian for Ubuntu. So this is that same bit of HTML, that same HTTP response. We can see that both in the system call capture as it writes it to the network, and in the network as we look at it in Wireshark. Now let's see what happens between these two events, between this read and the write. What I've got, I see an open at with the file var www html index.html. And if you've messed with Apache at all, you know that is the default location for that default index page. So we can see Apache read in this HTTP request, and now it is taking action inside the system to respond to it. So it opens that file, and then it doesn't read it. It does this thing called mmap. That is a memory map, and what it's saying is, kernel, I don't want you to copy all of this stuff to me, the worker process. I want you to throw it in some random memory location and then give me a pointer to that location. This, as I've done my research on it, is something that helps the system scale. If the kernel is maintaining this file in this shared memory location for one process, when Apache gets now 10,000 simultaneous requests for the same file, instead of every one of those threads opening that file and doing the read and copying it up to their stuff and then writing it back to the network, the kernel just says, grab it here. Easy. So we do that, and we can actually see in the response here, we can get into all of these details and see in the arguments, the result is just this long string of numbers, and that is the memory pointer. So that is the memory location where this file has now been copied to. And we can see some other things. We can see a write to the access log, so we can see exactly how Apache has logged this thing. A lot of good stuff here. And we can actually see after this, I find this one really fascinating. Apache finishes up, closes out this index file, and then immediately does another read off that network. And it returns nothing. We can see there's nothing in the bytes here. That buffer length column here indicates there was nothing being passed back. So why is Apache doing a read? Why is it reading nothing? And so there's this feature in HTTP called pipelining. And it's the idea that, hey, when I send a request, I don't have to wait for a response to send another request, right? If your browser is rendering an HTML page and there's references to 5 different JavaScript files and 10 CSS files and 30-something images, your browser can just request all of that stuff at once, and the web server can give each asset back in time. So in case that's happening, while the server was processing this one request, there's always a chance another one came in and is just sitting there in the socket waiting for Apache to take it up. So it's going to make sure that it's not missing anything and do that extra read. So that thing that looks extraneous at first glance is actually a really important part of the scaling design. And we can actually see here some more epoll p waits. So this same thread, once it says there's nothing for me to do, I didn't read anything back, nothing to happen, let me just wait for something to happen that I need to deal with again. I think this opens up a bunch of possibilities, because one of the things that I notice is if I start all the way back here when we accept the connection, there's this really fun feature. If you right-click and then click this Set Time Reference button, it's going to turn this time column into a stopwatch. This right here is just like hitting the lap button on a stopwatch. It restarts the time from 0 right here and then cumulatively counts up. So I want to look from the time that we accepted the request to the time that we wrote the response out, 495 microseconds. What was that? That is this right here. So I'm looking at the time of the write of the response back to the network, starting from the point where we accepted the network connection. Now this is really interesting because we saw in Wireshark the network response, or the application response, was 618 microseconds. So we're missing fully 1/6 of whatever's happening. So before, when I'm just looking at Wireshark and I see that 618 microseconds, I can say some of this is probably spent in the kernel, where the kernel's dissecting it's stripping away the headers from this packet and figuring which process to send it to and doing all that stuff. And some of it is probably the application doing these sorts of things that we're looking at to respond to it. And then there's actually a really nice PhD dissertation out there that did some experiments on how Linux handles load as things scale out, using kernel modules to do timing analysis on different points in the kernel. And it found that as things scale up to be really unsustainable, the place where requests seem to sit is actually in the socket, in that buffer between the kernel and the application. And so now we have 100 microseconds missing. It could be in the kernel. It could be in the socket. We don't really know right now, but this at least helps us narrow things down. If we say, if the total response time that we see on the network was 3 seconds, and Apache is still showing 495 microseconds, now we know the network is not the issue, and clearly the application is not the issue. This is an OS issue. And so now we have a lot more information and a lot better detail to help us dig in and solve that particular performance problem. So while we don't see everything, I think this is a really powerful tool that at least gives me some insight that I have not been able to see before in my work. Any questions on these capture files? Yeah, we should pass the mic around for this one, I think.
No, I know. Okay, so first question, SCAP file, maybe I missed it. How did you capture that?
This
That's
is
the first
with
step
that
too.
sysdig tool.
Oh, so that was, okay. So
That's
the
the sysdig
sysdig tool is the once you got your dump and then you're analyzing the dump offline and
Exactly.
kind
So
of offline, but
sysdig is installed on the web server.
right.
And I was running this command sudo sysdig -w http syscalls.scap and pulled that file off of the web server, and I've opened it right here.
Excellent. And to somebody who's like lived in S-Trace for a long time, I love this, but this is one process. Does it enable the essentially, I mean, it's not S-Trace, but does it enable combining processes?
So by default, sysdig will capture every process on the system. There's filtering logic you can put into the sysdig command to limit things down. And actually what I've done for this capture file in particular is once I've filtered it to Apache, just Apache stuff, because this started out as everything. And there's this nice option up here. If I go to File, Export Specified Events, this is going to save off just the stuff that I have filtered. And so it's an easy way for me to cut down on the file size and the steps in order to get to some insight for a demo like this. But this file started as everything that was on the system, including sysdig itself. Sysdig was logging its own stuff in the SCAP file.
Compared to core dumps, last one.
I do not do much with core dumps, I'll be honest, so I can't give you a good comparison.
Is there a way to do this semi-real time? Like actually as the process, because like I've done where you inject them into your cluster and then all the PCAPs get done in semi-real time. I mean, on a small scale, is that capable of doing that?
Yeah, so the sysdig tool does support, it's called ring buffer or something like that. And so you can set up sysdig to just save off files every 5 seconds and then come back and combine them up here. The secret sauce with the SCAP file, it's secretly a pcap-ng file under the hood. It just has a different file extension. So if you've used things like editcap, mergecap, and that sort of things, the other tools that come packaged up with Wireshark, those will work for SCAP files too. So if you have my one 5-second file here, my other 5-second file here, you can run mergecap and spit them into one single output file for your analysis. Anything else? All right. So I had 2 quick questions. So the first one was, sorry, say that again. First one is how big are the files? This one that was a couple minutes, that was just a couple meg. Unfiltered was a couple meg. This one right here is a handful of kilobytes. Yeah, they're relatively efficient for what they are. And the other question was kernel traces, and the answer is no, because it is strictly system call stuff. The way that Stratoshark is being developed, though, if we have a standard output template for kernel traces, there's no reason that Stratoshark couldn't support that in the future. So if that's something you want to do, and it's something I'd be interested in too, the Wireshark Foundation maintains its Git repo on GitLab. Find it, submit an issue. You can tag me in it. I'm just Josh Clark on there, and I will go and upvote the crap out of that thing so we can get that going. Yeah, absolutely. We have just a couple minutes left, so let me wrap up real quick, and then we can do some more questions after the session formally ends. So, like we've just kind of gotten to, there are some limitations right now. The big ones I see is we're unable to see interprocess and some kernel communication. So when there are statically linked libraries, say Nginx and Apache with OpenSSL for TLS communication, we don't see that crosstalk. So That's the whole thing. Encrypted thing comes into Apache. It passes it to OpenSSL to decrypt, and then send that decrypted clear text back up to Apache to handle. We don't see any of that. We just see the first encrypted thing come off the network. We're also missing shared memory locations. So that mmap, that memory map that we looked at, we don't get to see what's in that. There's another one that I look at quite a bit called get directory entities, so get dents. That passes back, it's basically the system call for ls in some ways. And the only response that we get is a pointer and a length. And you know, even strace gives us more information than that. So strace for that particular call will actually do a little bit of math on the length that we get back and say, yeah, we probably are getting response for something like 150 different files and directories. So sysdig is missing those features as well. So what I'm thinking is this is early stages. We're still building up. As we identify holes, we open issues in GitLab, and we'll get stuff resolved. But the biggest one for me right now is that there is no capture support for Windows or Mac. You know, I can do a whole lot of work at work right now with sysdig and Stratoshark, but as soon as something hits a Windows server, I'm blind. So Windows has Procmon as a process monitor that does something similar to what sysdig does. And so I have an issue open with the Wireshark team to start seeing if we can incorporate Procmon capture files the same way that we have sysdig capture files. So I'm just trying to get stuff going as wide as we can, patch holes as I see them, and of course share the good news of this new tool with y'all. Now that's going to wrap things up. Happy to field more questions. And then also, that QR code goes to our conference schedule, goes to this is the feedback link. I always want to know what I've done well, what I haven't done well, what I can do better in the future. So please feel free to let me know that sort of stuff there. Thank you very much for the time today, and I'll be hanging out here all night, so come bother me about Stratoshark stuff.